Okay, so chapter 12 is the introduction to the analysis of variance. So, the analysis of variance is used to evaluate the mean differences between two or more treatments or populations. It uses sample data as a basis for drawing general conclusions about the population. And this test has a clear advantage over a T-test because it can be used to compare more than two treatments at the same time. So if we take a look at figure 12.1, we can see a typical situation when an analysis of variance, which is also called an ANOVA, would be used. So we can look at population 1 with the first treatment, population 2 with the second treatment, and population 3 with the third treatment, and we can compare all three of them. So, for an analysis of variance, we'll have a factor, which is the independent or quasi independent variable that designates the groups being compared. We also have the levels of the factor, which are the individual conditions or values that make up a factor. And then we also have a factorial design, which is a study that combines two or more factors. We also have the null hypothesis, which is the treatment conditions that have no effect on the participant scores. And in the population, this is equivalent to saying that the group means do not differ from each other. And you can see the formula that we would use to calculate the null hypothesis. We also have hypothesis 1, which says there is at least one mean difference among the populations, and the treatment conditions do affect the scores, and it's the acceptable shorthand for not having the null hypothesis. The issue is how many ways can the null hypothesis be wrong? By all means, they're different from every other mean, and some means are not different from some others, but other means do differ from some means. We can have type 1 errors and multiple hypothesis tests. If that is the case, the ANOVA can compare those means better than the T-test, and these experiments often require multiple hypothesis tests, each with type 1 errors and their alpha level. And then the type 1 error for a set of tests accumulates test-wise alpha, and the ANOVA evaluates all mean differences simultaneously with one test. And that's going to be regardless of the number of means, and thereby avoids the problem of an inflated experiment-wise alpha. For the test statistic for an analysis of variance, it's not going to be possible to compute a sample mean difference between more than two samples. You've got the F ratio, which is based on variance instead of sample mean differences, and that variance is used to define and measure the size of the differences between sample means. The variance in the denominator is going to measure the mean differences that would be expected if there was no treatment effect, and that formula is going to look like the one you see on the screen. Differences between those sample means and the differences expected with no treatment. When we have between treatment variance, that's going to be variability that results from general differences between the treatment conditions. This variance between treatments measures differences between those sample means. And when you have a within treatments variance, that is the variability within each sample, and those individual scores are not the same within each sample. So if we look at figure 12.2, we can see that total variability that's partitioned into two components, the between treatments variance and the within treatments variance. The F ratio can be calculated after we have analyzed the total variability into two basic components. The denominator of the F ratio is called the error term, which measures only those random and unsystemic variability scores. The value obtained for the F ratio is going to determine whether any treatment effects exist, and there are two possibilities. There's no systematic treatment effects, which is the differences are entirely caused by random unsystematic factors, and the treatment does have an effect and causes systematic differences between samples. If the null hypothesis is true, the size of the treatment effect is near zero, The F ratio is near 1 and indicates that the differences between those treatments are random and unsystemic. If the null hypothesis is true, then the size of the treatment effect is more than 0, and the F ratio is noticeably larger than 1, and there are systemic treatment effects also present. So let's go ahead and do a learning check. True or false? An analysis of variance allows researchers to compare several treatment conditions without conducting several hypothesis tests. And if the null hypothesis is true, the F ratio for the analysis of variance is expected on average to have a value of 0. Take a few moments to think about what might be the correct answer. And the correct answer is true and false. There are several conditions that can be compared in one test for an analysis of variance. And it's false that if the null hypothesis is true, the F ratio will have a value near 1, not 0. So when we have the analysis of variance and we use notations and formulas, the number of treatment conditions are indicated by K. The number of scores in each treatment are indicated by N1 and N2. The total number of scores is N, capital N. When all those samples are the same size, then N is going to equal KN. The sum of scores for each treatment is T, capital T. And the grand total of all scores is capital G and sum of capital T. There is no universally acceptable notation for an ANOVA. Other sources could use a different symbol because it's not universal. So here's an example in figure 12.3 of the structure and sequence of some calculations that can exist from an analysis of variance. And then in figure 12.4, you've got the partitioning of the sum of squares for the independent measures of ANOVA. And that's the formula that exists for that. And then the analysis of sum of squares formulas are here as well. When it comes to degrees of freedom and the analysis of variance, the total degrees of freedom are going to be DF total, and that's going to be capital N minus 1. The within treatments degrees of freedom is going to be DF within, and N minus K, capital N minus K. And then the between treatments degrees of freedom will be DF between and lowercase K minus 1. And then in figure 12.5, we can see how those formulas would look for each of those different degrees of freedom samples, and then how we would also calculate those as well. So let's go ahead and do another learning check. An analysis of variance produces the sum of squares total that equals 80, and the sum of squares within that equals 30. For this analysis, what is the sum of squares between? Give you a couple moments to think about what the between number might be. And hopefully you came up with answer A. That's going to be 50 if you put it in that formula. If the null hypothesis is true, the value of F will be around 1. And because F ratios are computed from two variances, they are always positive numbers. The table of F values is organized by 2 degrees of freedom, the between and within degrees of freedom, which are shown in tables and rows. And here's an example of figure 12.6 with the distribution of the F ratios with the degrees of freedom at 2 and 15. Hypothesis tests use the same 4 steps that have been used in earlier hypothesis tests, and those computations of the test statistic capital F is done in stages, and those 3 stages are listed below. Having a concise method for presenting the ANOVA results is necessary because it helps organize and direct the analysis process. It's convenient for checking computations, and it's the standard statistical analysis program that uses output. To compute the percentages of variance accounted for by the treatment conditions, we have to measure the effect size for the ANOVA. And in published reports of the analysis of variance results, the effect size is usually called lowercase n squared or eta squared. And you can see what that formula looks like on the screen as well. And when we want to report the results of the ANOVA, the treatment means and standard deviations are presented in text, table, or graph, and those results are summarized um, using the methods that are shown on the screen, for example. When we make assumptions about the independent measures of the analysis of variance, we have the observations within each sample that must be independent. We have the population from which the samples are selected, which must be normal. We have the populations from which the samples are selected that must have equal variances, called the homogeneity of variance. And we have violating the assumption of homogeneity of variance is going to risk invalid test results. We also can have post-hoc tests, and the analysis of variance will compare all those individual mean differences simultaneously in one test. It gives us a significant F ratio that indicates at least one of the difference in means is statistically significant. That does not indicate which mean is significantly different. But a post hoc test is a follow-up test done to determine which of those mean differences are significant and which are not. Post hoc tests can compare those two individual means at a time. Each comparison includes a risk of a type 1 error, and that risk of type 1 error accumulates and is called the experiment-wise alpha level. Increasing the number of hypothesis tests increases the total probability of a type 1 error. And those post hoc or post tests use special methods to try to control those experiment-wise type 1 error rates. Tukey's honestly significant difference, or HSD test, is a single value that determines the minimum difference between the treatment means that is necessary to claim statistical significance, which is a difference large enough than P is greater than A. Then there's the formula for the honestly significant difference. The SHAVE test is one of the safest of all possible post hoc tests because it protects from type 1 errors, and it uses an F ratio to evaluate the significance of the difference between any two treatment conditions. So here's another learning check. Which combination of factors is most likely to produce a large value for the F ratio? So I'll give you a few moments to think about that. And the correct answer is going to be B, a large mean difference and a small sample variance. Here's a true false. Post hoc tests are needed if the decision from an analysis of variance is failed to reject the null hypothesis. And a report shows that analysis of variance results are indicated, and you can conclude that the study used a total of 30 participants. Give you a few moments to think about the correct answers here. And we have false and true. A post hoc test will be used only if you reject the null hypothesis. That means that one of those differences is significant. And it's true that if you have the degrees of freedom that were the ones indicated, then it would tell us that there was 30 participants who participated in the study. The numerator of the F ratio always measures how much difference exists between those treatments, and the denominator of the F ratio measures how much difference exists within those treatments. And we can see here from figure 12.7 a visual representation of the between treatments variability and the within treatments variability that can exist with analysis of variance. For two independent samples, either T or capital F can be used. It always results in the same statistical decision. The T statistic compares the distances, while the F ratio compares variances. And the relationship is capital F equals T squared. For any value of the critical region, we'll also have T critical squared equals capital F critical. And here's an example in 12.8 of the distribution of those T statistics with the degrees of freedom at 18 and the distribution of F ratios with the degrees of freedom at 1 and 18. Here is figure 12.9, which shows the formulas for an ANOVA. And I hope that helps you understand everything about the analysis of variance.